in this final section of the chapter, I will come to a medium access technology that is quite different from the others. And I mentioned this code division multiplexing already in chapter 2. And now I will give you an example how it works. I always said, okay, let's postpone this a bit to chapter 3 and there we'll explain it. So code division multiplexing, and then the access scheme is CDMA, code division multiple access, is different, usually not used in wired system, but quite important in wireless system, because the majority of third generation system in mobile communication, cellular networks uses CDMA technology. It's different now in fourth, fifth, etc. generations. I will explain later on why this is the case. So, when I explained CDM, code division multiplexing, I told you that now all terminals send on the same frequency. So we all use the same frequency, send at the same time, same space. And we use a whole bandwidth of a transmission channel. Okay, but how can I then separate different senders? The basic idea is you have a kind of a uniqueness. For example, a unique random number, and the sender XORs its signal with this random number. I will give some more details to this randomness later on. And then the idea is the receiver can tune into the signal if the receiver knows the random number and the pseudo-random number sequence you generate based on this random number. How this is done, it's called correlation. I will not go into the details, but briefly explain how it works. Before I give you the example, first of all, the disadvantages, and to be honest, this is also why today in the newer systems, CDMA, well, is not that prominent anymore. It's a higher complexity, yes, and you have to know this random number, okay, this could be also a secret, but then you have to tune into this signal and you have to correlate something, you have to recalculate the original signal, so you cannot just listen to the medium and then start receiving. Okay, but this can be done, but then we really have a problem. The signals should have the same strength at the receiver. Remember near-far terminals, remember breathing cells. Quite typical for CDMA technology is that you have to have a really good power control. So all the terminals, when they send their data, their signals to a receiver, they have to fine control the output power. At the receiver, all signals should reach this receiver the same strength. Okay, so this is really a bit complicated. Think back of planning of the cells. If you have these breathing cells, for example, the change in the signal power depending on the surrounding of sender and receivers. There are big advantages. So everyone uses the same frequency, you don't need any planning. Remember cell planning, frequency planning, when we had these hexagon patterns in our cellular networks? We don't need this anymore. So the classical CDMA network, all the terminals and all those cells operate on the same frequencies. What is also quite nice is that we have a huge code space because we separate users in code. That's way bigger compared to frequencies, for example. Also a good thing is that interference is not coded, so white noise, for example. And you can easily integrate forward error correction and encryption. Why? Well, I already mentioned the party example when I talked about code division multiplexing. Remember, you're on a party and you talk to someone else in English. Then there's a couple talking in German, some others in Finnish, some in Japanese, Chinese, for example. The point is as long as those languages, well, do really have nothing in common, it's usually no problem to have your conversation and in parallel, same time, same space, same frequency, another conversation, for example, in Japanese. But as soon as the languages are too close to each other, for example, American and British English, well, that's very close, but also, for example, Dutch and German, then you will understand parts of the conversation. That means there's a lot of interference. And here in CDMA technology, we want to have so-called orthogonal codes, or more or less orthogonal codes. And for languages, this means they have really nothing in common. They are orthogonal. But, well, for example, British English, American English, or Dutch and German, even Swedish and German, well, they're not really orthogonal. But Finnish and German, or Finnish and Swedish, they are really orthogonal. So, the problem is we have to find some kind of orthogonal codes. And if we use them, those codes, or even orthogonal pseudo-random number sequences, we can encode our data stream using this pure digital algorithms. And then the resulting signals are orthogonal. And by using the right technology, we can recalculate the original signal. Think of the party example. Now I want to show you a very, very simplified example of how this works, that you can at least have some kind of a basic understanding. There are really great books about CDMA technology. Andrew V. Turby and others wrote the classic books about this, but here it's enough to understand the basic idea. Let's assume a sender A. Now this sender A wants to send, in this very simple example, 1 bit. AD is a single bit. We want to transmit this bit with the value 1. And here we also use a very short key, a key. This key is only 6 chips. Maybe you heard the terms chip. Think of chipping sequences and spreading the spectrum, spread spectrum technologies. And now you suddenly see how this all belongs together. With the help of a certain orthogonal code, we can automatically spread our spectrum. Why spreading? Because we want to avoid narrowband interference. Plus, if we do this spreading using a secret code, this spread signal is nothing but noise for the others. That means CDMA combines the spreading and encryption using a secret code. Okay, now for this simple example, very short code. In reality, codes can be way longer, 256 chips or even longer, resulting in spreading factors of 256 or even more. For military applications, you can spread factor of 10,000, whatever. Now to make life simpler, we simply say, okay, 0 is represented by -1 and our digital 1 is represented by +1. Now we send a signal. That is exactly our spreading, but now with a special code. So spreading, that means bitwise multiplication. Now our bit is the 1. We multiply with our key. So 1 multiplied by -1 equals -1, etc. So the resulting vector, our signal, is -1 +1 -1 -1 +1 +1. Okay, so spreading factor in this case is 6. Okay, now we do the same for another sender. Here we want to send a bit with the value 0. We use again a key of 6 chips, 1 1 0 1 0 1. Then we calculate our sending signal. -1 -1 +1 -1 +1 minus 1. Now what happens when we send both signals over the air? Again, simplified example, no noise, and we assume we send those signals starting at the same time. So, well, both signals simply superimpose. So, neglecting interference, the resulting signal now is AS plus BS minus 2, 0, 0, minus 2, plus 2, 0. Oops! So you see how those parts of our bit, parts of the signal, cancel out each other. Here, but here as well. So that means although in the original signal there was some information, you see here, plus 1, minus 1, or here minus 1, plus 1, these parts, they cancel out each other. So now we have a problem, maybe. So now we have the superimposed signals and with some cancellation of the signals and some amplified parts, etc. So how can we then recalculate the original data? Quite simple. The receiver wants to receive now, let's assume this, receive the signal from sender A. The receiver has to know the key, AK. Now calculates the inner product. That means you apply the key AK to this received signal. So we have our signal, inner product with the key AK. Inner product, so you take here each component minus 2 times, you see our key is minus 2 times minus 1 equals plus 2. 0 times whatever equals 0, 0 times whatever equals 0, then minus 2 times minus 1 is plus 2, then again plus 2 plus 0. The result is 6. 6? I thought we want to calculate our bits. No. The point is, now, in this case, by convention, we simply say, okay, the result is greater than 0, then the original bit was a 1. We do the same for receiving the signal of B. We multiply with the key of B, and we get a nice minus 6. And if it's less than 0, we say this must be a logical 0. Okay, so this is basically what the correlation does. More next slides. Simplified example, but that's the basic idea. So you have 2 keys, each sender has a key, and the keys should be orthogonal. What does it mean? Remember math? Calculate the inner product of the 2 keys. What's the result? Well, again, the key 0 equals minus 1. That is, so minus 1 plus 1 times 1 is plus 1. And then we have minus 1 plus minus 1 is plus 1. Minus 1 plus 1 is minus 1. And then we have, again, plus 1 times minus 1 is minus 1, and plus 1 equals 0. That means we have perfect orthogonal, think of vectors. They are orthogonal. That was the definition of when are 2 vectors orthogonal, if the inner product equals 0. That was the definition. And here in this simplified example, perfect world, we have perfect orthogonal vectors. So the inner product is 0. Great. And this is why this example works so nicely. I know, in real world we have interference. We do not start sending at the same time, etc., etc. This is why in real world we might have errors receiving the data. This is why we have forward error correction and so on. Once more, a simple example. Now shown using signals. Very short keys. This example here is our key, but we use a sequence. We do not have to repeat the key as I showed you in the previous example, but now we have a kind of a pseudo-random number sequence, and we do again the XOR of our data with the sequence, and the result is a certain signal. In real life, longer keys, etc. But that's the signal. Now we take this idealized. Again, you know, we don't have really these signals, but that's to just give you the idea. Now we take this signal, and now here we do the same for B. We have a signal B. And now we superimpose both signals, AS plus BS. That's what we send over the air in an idealized word. Okay, we know we have to apply many other things, modulation, etc., etc. Now, how do we find out what, in the end, the original data was? The receiver does not know anything about the original data. That's just for you, for comparison. So we don't know this. Now we receive the signal. That's the signal that comes in, okay, in real life, etc. Think of noise. We again apply the key. That means we calculate the inner product of the received signal, the sum of the two signals we've just sent. Inner product. And now, just to explain it in an easy way, think of an integrator. In technical terms, it could be a capacitor, for example, collecting either, well, positive or negative signals. Now think of my signal. Let's say if this is the zero line, this is negative and this is positive. Now let's say I have got an integrator that integrates over a time period of 1 bit. So I integrate my signal. That means, here the signal is negative, then the signal is 0, it's negative, 0, negative. The result here is, for example, in a technical way, negative voltage in a capacitor. I, in this example, interpret this as a 1. In the other example, it was a 0. That's just the convention what we do. And the next step, for the next bit, we integrate, and you see here it's positive, positive. We integrate, it's a 0, stays the same. It's positive, stays the same, positive. That's strong positive value. This is why we have a 0. And here again, negative value. This is why we have a 1 again. So that's the idea. So what happens if we do this to the other signal? Not a big surprise. So up to here, it's all the same steps, but now we create the inner product with a key of sender B. Again, we have our integrator here, and the integrator now can easily recalculate the bits that we just sent. Okay, but what happens if we do not have the perfect key? There will be a result. So let's go for this final example. Again, that's a superimposed signal here, but now we have a wrong key. That means we do not know, for example, the secret key. What happens there? Again, we calculate the inner product here with the wrong key. What happens at the integrator? Negative, that means we go down, so we stay here. Oh, positive, so we go up again, positive, a bit up, 0, bit up. So yes, this is positive, so we code this as a 0. Not that strong would be here, but still. Something similar happens here, so the outcome will also positive, weak, but might be 0. Here we have nothing, so we don't know. So you see, yes, there will be a result if you use the wrong key, but you cannot recalculate the correct data based on these results, because sooner or later you will have something like checksums and they will simply fail. Because some flipped bits and the checksums will not work. And forward error correction, yes, it works, but only to a certain limit. So if you do not have the key, the idea is that, well, if you have secret keys and long sequences, you cannot guess the key. And then if you just use an arbitrary key, you will have an output, but it's not possible to recreate the original code words. So that's basically the idea. Well, again, similar to the example, if you know some words of Finnish, you might understand a bit, but too many errors. But maybe it works if you know German and someone speaks in Dutch, maybe you will understand most of the conversation. So that's similar, that's a different. So that should be all for the CDMA technology for computer scientists. Please do have a look into the books if you're more interested in how this works, but this requires a lot more of understanding in electrical engineering. With CDMA, you can also do some more fancy things, like, well, combine it with Aloha. Why not? So we learned that Aloha is not really efficient. We also learned that CDMA, well, looks a bit more complex. There's something like integration, correlation, etc. So that's not that simple technologies. We have different codes, etc. So the idea here is of the spread Aloha multiplexes, use only one single code, again the chipping sequence, to spread the senders. So the classical Aloha would be, well, we spread our data over a longer time. So 1 is relatively long. Put certain energy into this bit to transmit it, but as soon as it overlaps, we have these collisions. So that's not that ideal. So the idea here is now we squeeze our bit into small spikes, very small one. We send for a short period but with higher power. And in the end, if the area is the same, that means the blue area is the same, we can transmit our bits. But that's also not a good idea. High power, short periods, some problems. So what we do now is we spread this again using a certain chipping sequence, 110101 in this case, spreading our small peaks, and you see how the first one, 1, 2, 3, 4, 6, 7 is now spread in time. And then, yes, there still might be collisions, like maybe here, like maybe here, maybe here, depending some. But this hits only a single chip. And using forward error correction, we can recreate the original data. So again, statistically, the chances of a collision are way lower compared to sending the bits as they are. So yes, you have to find a good chipping sequence, but that's basically CDMA technology without the CD. So there's no really coding. We use the same code. That's just to avoid the collision in the Aloha scheme, the classical Aloha scheme. Okay, you see there are many different ways of performing this multiplexes, and when you compare them, you will easily see the different ideas for the classical schemes: SDMA, TDMA, FDMA, CDMA. So classical schemes, yeah, you can also use the polarization in addition. So can be done. You can always add this to all the other schemes, but you should at least understand the basic idea of S, T, F, C, and PDMA, and what you actually separate. You separate the space, you segment the time or the frequency, or you use orthogonal codes, and how this can be used, how you separate the different signals. You filter in frequency, you have to sync in time, so these are differences. Or you have to know the code, need special receivers, and they all have their advantages and disadvantages. So flexibility with a simple SDMA scheme, well, you have antennas separated. For TDMA, you need precise synchronization for higher data rates. Yes, for FDMA, it's not as flexible, but you can combine it. I talked a bit about OFDMA. That's, for example, a combination. Or the 3G systems, they combine CDMA with TDMA and FDMA. So depending on how you look onto a system, you quite often see these combinations. You do not use a single form of multiplexes. Quite often you have certain frequencies and then you use some time multiplexing in addition. That's just a brief overview, a comparison of the schemes. So, finally, some questions and some tasks for you. Again, think back of near-far effect. How does this influence TDMA system and what happens in CDMA systems? So what are the differences? What are countermeasures in TDMA systems and what about CDMA systems? Think back, there are differences, different consequences. Then who is actually responsible for MAC in SDMA? What are roles of mobile stations, base stations, things like this, planning of network providers? And then think of different terms like interference. What does interference mean if you use S, T, F or CDMA? What are the countermeasures? Think of the different MAC schemes and think of hard guarantees. Can you give some hard guarantees? Okay, I know if you have a jammer, wideband jammer, you cannot give any guarantees. But under normal circumstances, can you give guarantees with what type of schemes? What are the guard spaces in CDMA? And then go back to this very simple CDMA example on slide 19. And now add some random noise to the transmitted signal. Just add this vector, 1, -1, etc. What can the receivers detect? Okay, now include a near-far problem. How does this complicate the situation? Just multiply the strength of the signal of one of the senders. What are possible countermeasures?